Okay, we talked about in chapter 4, structure of the atom. Now in chapter 5, we're focusing on the electrons. But we are going to take a little bit of a departure and talk about light and waves first. So it's a little bit different than what we're doing, but in the end, it will all tie together. So the first section is light and quantized energy.
You will need your calculators for this section.
Yes.
So if you don't have
Maybe
it,
pause.
go get it, come back.
Okay, electromagnetic radiation. That's a form of energy that exhibits wave-like behavior as it travels through space. So below the writing, you got the electromagnetic spectrum. It goes from gamma rays all the way to radio waves. Now you'll see the spectrum going in both directions. So you may see radio waves on the left side and not on the right side. It's fine, it's the same spectrum, it's just going by frequency or by wavelength. So some types of electromagnetic radiation are gamma rays, X-rays, UV rays, infrared, visible light, microwaves, and radio and television waves.
And satellite.
Yes, there are lots of types of waves. Let's talk about characteristics of waves. So first one is wavelength. So that little symbol there is lambda, and it's the distance between crests or troughs of a wave. So if you look at the diagram, the top part of the wave is called the crest, the bottom part is called the trough. You're just measuring between those points. And it's either measured in meters or nanometers. Nanometers are 10 to the negative 9th meters. Look on your cheat sheet if you're having trouble with that.
All the way down here.
I would say the biggest problem when it comes to these types of calculations is students forget how to convert their units. So that's the biggest thing. Frequency, that is the Greek letter nu, and it looks like a V, just a fancy V. But it's the number of waves that pass through a point in 1 second. So the units are going to be hertz, or it's per second, 1 divided by seconds. So if you were staring at a particular point and you're watching waves come through, you're seeing how many go through in 1 second. Now the amplitude is going to be the wave's height from the origin, or the center of the wave, to the top of the crest or bottom of the trough. So it will be the exact same for the crest or for the trough.
Yep.
If you take physics, you'll learn all about this. Wavelength and frequency, they are related, but they are inversely related or inversely proportional. So as your wavelength decreases, your frequency gets bigger. So if you look at the top picture, the shorter wavelength, you've got really skinny waves going through. If you were to focus on one point and watch those waves go through, frequency would be a lot higher. Underneath is a longer wavelength. You can see that the distance between the crests is a lot larger, so you have a long wavelength and you have a shorter frequency. So it's going to be a lot slower coming through.
I like to think of them kind of like if you were to think of a pitch, where those waves would hit the shorter wavelength would be a much higher pitch and more annoying, so it's more frequent, larger frequency.
Yes.
And then you've got your longer wavelength, so it's like the low one, slow one. So it's got the longer wavelength, the shorter frequency, okay? Or annoyance scale.
Okay, let's talk about speed of light. The speed of light in a vacuum is a constant number. It is 3.0 times 10 to the 8 meters per second. So this is on your cheat sheet, but it's also very easy to memorize. But again, you don't have to.
Yeah, it's on your cheat sheet.
The symbol is c. It's a lowercase c. And the equation that goes with speed of light is c equals wavelength times frequency.
There you go.
So let's do a calculation. What is the wavelength of a microwave that has a frequency of 3.44 times 10 to the 9th hertz? So we're going to fill in our equation here.
Well, we always know C. It's always a known value as the 3.0 times 10 to the 8th meters per second.
There you go.
So we always know C. So in these equations, if you're finding out wavelength or frequency and you're given one or the other, you're going to have then your frequency, you're going to find your wavelength, so that's your unknown value. Plug in your 3.44 times 10 to the negative 9th hertz. Oh, I'm sorry.
Oh, it's just a regular.
Hertz. Yeah, just
positive.
Yeah, sorry. Now, because Because your wavelength is over on the right side, we need to get rid of the 3.44 times 10 to the ninth. So these problems you're going to be dividing every single time.
Yes.
So they're actually pretty easy because you just have to divide 3.0 times 10 to the 8th divided by whatever else is coming at you.
And it's only 3 variables, so you could use your little triangle if you use triangles to help you manipulate equations. So we're going to do 3 times 10 to the 8th divided by 3.44 times 10 to the 9th.
You get 0.0872.
So what are our units going to be here?
Because it's a wavelength, and wavelength is a distance value from crest to crest, it's got to be the meters.
Yes.
And the hertz end up actually canceling each other out with the hertz on the bottom and the seconds that was being divided.
Yeah, remember hertz is just 1 divided by seconds. So if you've got seconds on the denominator over here, it's going to cancel out. And all you're left with are meters. So if you want your triangle, let me draw that really too fast, maybe. Okay, so C would go on the top, and then wavelength and your fancy V.
Yeah, that's pretty good.
Yeah.
All right, moving on.
Okay, the electromagnetic spectrum, we already talked about this a little bit, but it includes all forms of electromagnetic radiation. As wavelengths get smaller, frequency and the energy increase. So we already know that wavelength and frequency are inversely proportional. Well, it turns out wavelength and energy are also inversely proportional. So as they get smaller, the energy goes up. So you can see the radio waves, they are really long, and in class we'll probably calculate a radio station and show you how long that wavelength is. You can see microwaves are a little bit shorter, infrared shorter. Visible light isn't that short comparatively.
But it's a small little portion on the scale.
But that is all that we can see. So all the other ones are pretty much invisible to us. But we know that they're there. UV light, that's responsible for a lot of sunburns and skin cancers. X-rays, they travel through skin, but not through bone. And gamma rays can actually travel through everything. So they have the most amount of energy here.
Yep.
Visible light, if you can't remember your rainbow, just remember Roy G. Biv. Okay.
But red has the least amount of energy. Violet has the most. If you can remember from your 8th grade stars charts, the blue stars have the most energy, the most heat given off. The red stars were your coolest. I like to think of it that way as well, to try to tie in other sciences.
I also look at, you've got infrared, that comes before the visible spectrum. So red is in that word. And then you've got UV, ultraviolet. Violet is on the other end of the spectrum.
Ooh, that's
so
a
it's
good one.
after the visible spectrum. So if you can't remember it, look at infrared, look at ultraviolet, and you'll figure out where the red and the violet go.
Nice.
Okay?
I like that trick.
Light and matter. So why do objects emit only certain frequencies of light at a given temperature? So this question comes up when, say you're heating a solid piece of iron, and you're heating it up and it turns red, and then it turns orange, and then it turns kind of yellow, and eventually it turns blue. Well, it's emitting different frequencies because it has different energies. Planck's theory, this is Max Planck, by the way, he's very serious looking, but his theory says matter can only gain or lose energy in small, specific amounts called quanta. So a quantum is the minimum amount of energy that can be gained or lost by an atom.
All right.
So it only gains it in increments. The photoelectric effect deals with electrons. So when light of a certain frequency hits a metal, electrons will be emitted from it. Specific wavelengths are for each specific metal. So it's either all or nothing. If your wavelength is too short, it's not going to actually allow an electron to be emitted. So if you see the red line, it does not have enough energy to actually emit an electron. The green line does, so that must be the threshold, and then the blue line makes it go even faster. Okay, and then this is Einstein's contribution. I love this picture of him, but he said that light has a dual nature, and a beam of light actually acts like a wave and a particle. So photons are particles that carry a quantum of energy and travel as a wave. So light carries energy with it and travels in a wave-like fashion. Okay, so frequency and energy. Frequency and energy are directly proportional. If one goes up, the other goes up. Okay, so again, these are inverse to wavelengths. So if either of these go up, then wavelength's going to go down. So here's your equation. This is your second one. So it's energy, capital E, equals H times frequency. So H is Planck's constant. Remember the serious guy from 2 slides ago? This is a constant, it's on your cheat sheet, but it's 6.626 times 10 to the negative 34th joules times seconds. What does joules stand for?
Joules.
What is the SI unit for?
The energy.
For energy, yeah. We haven't talked about energy yet. So remember, your energy unit is going to be joules, capital J. So let's do a practice problem. What is the energy of a photon that has a frequency of 7.230 times 10 to the 14th hertz? Okay, so we're going to fill in our equation.
What's the energy? E equals, that's our unknown.
Mm-hmm.
And we always know H is 6.626.
Oh, no. Just go. 626.
Times 10 to the negative 34 joules per second. No, it's not per, is
Yeah.
it?
Okay.
It's times second.
It's times
Per
seconds,
would
'cause
mean
it has
it's
to cancel.
dividing.
Okay.
Oh,
And
times.
then times 7.230
Mhm.
times 10 to the 14th hertz.
All right, so the hertz and the seconds are going to cancel, and you're left with
Mhm.
just the joules.
Yep.
And we just have to multiply those together, and we end up with 4.79
Mm-hmm.
times 10 to the negative 19th joules.
Good. Okay, make sure you label it, and make sure, I've had a lot of students, they do not actually put the exponent on there, or they leave out the times 10 to the, so if you give me 4.79 joules, that's incorrect. Okay,
Yeah.
you got to make sure you have 4.79 times 10 to the negative 19.
Yeah, look all the way down your calculator. It'll be at the very end.
And it may just be a small number at the top. It may not say 10 times.
Yeah.
Or it may say E.
Oh, yeah.
Okay. So that's how you use that equation. Now let's combine the equations. Okay. So what's the energy of a microwave photon that has a wavelength of 0.125 meters? So first we have to find the frequency. So what was that first equation that we had?
C equals the upside down Y
Mm-hmm.
times the nu.
Mm-hmm.
All right, so we always know C, 3
Yeah.
times 10 to the 9th.
Is it 9th or 8th?
Oh, crap. It's the 8th.
Okay. Yes, I was right. Darn it. Times 10 to the 8th. And that's a 3, not a 30.
meters per second
Okay.
is equal to, we want to find frequency. So this is wavelength, so we've got our 0.125 meters that we can plug in that upside down Y spot in the lambda.
Mm-hmm.
Now we're going to divide.
Yeah.
That's an equal to.
Yes.
All right, so 3.0 times 10 to the 8th divided by 0.125 meters gives us 2.4 times 10 to the 9th. That's where I got the 9. Hertz.
Okay. All right. Now, what are we actually looking for? We're looking for the energy. Okay. So you were given the wavelength, but in the energy equation, you don't use wavelength. So that's why we had to go back and use that speed of light equation, because we had to find the frequency somehow so we could plug it in here.
Because the frequencies are a common factor between the two that tie them together.
Mm-hmm.
All right, so we want to find the energy, so we're going to keep our E.
Uh-huh.
Planck's constant, 6.626 times 10 to the negative 34 joules times second, times our answer we got up above, 2.4 times 10 to the 9th hertz. And those are multiplied together to give you an energy of 1.59 times 10 to the negative 24th joules.
Very good.
Yeah.
Okay, atomic emission spectra, we need to talk about this because we will do a flame test lab that involves this. So when atoms absorb energy, they become excited. Now, the excited atoms need to return back to their stable state by emitting light, which in turn releases energy. We'll get more into how they actually emit light. But the atomic emission spectrum is unique for each element and can be used to identify it. It's a set of frequencies of waves emitted by atoms of an element. So below we have the hydrogen line spectrum. When it gets excited, these are the colors that will basically be emitted. So if you are looking for these colors, then you can identify them on the emission spectra or the absorption, and you'll be able to determine that you're actually dealing with that element.
All right. Each one is individual, so it should be pretty easy.
And when you do compounds, you'll be able to find the individual elements too.
Excellent.
Okay,
Section 1 done.
yay!